You're welcome to day 23 of 50 days of tutelage. And in today's class, I'll be teaching you about equilibrium and moment. So let's get right into it. What is equilibrium? We have discussed so many things. We talked about motion. So we talked about the concept of motion. We talked about Newton's law of motion. And then we also discussed about forces, which are the agents that actually cause motion to occur. But what is equilibrium? Another thing we also discussed about is that we discussed, so I'm going to be kicking off right from this place. We discussed about the concept of resultant force, the concept of resultant force, or what we also call net force. And I told you that whenever you are dealing with force in physics, you will always have to deal with what we call net force. You don't just deal with force in an isolated way unless the force itself is isolated. That is, it is the only force in the system. Now, the concept of equilibrium is going to be predicating on that particular idea as well. And what is the idea? The idea is that equilibrium means to balance. So, the concept of equilibrium is bringing in balance. Now, force or resultant force in this case, what is the function of force? The primary thing is that it causes motion to happen. Now, if force is causing motion to happen, then if I'm going to create a balance, then what is going to happen is that there's going to be a kind of inhibition to motion or inhibition to the way a body is moving or the inhibition to the way a body is going to change the way they want to move or the way they are moving. So if you go back to Newton's laws, the first one talked about the fact that if you're at rest, you will always be at rest, except a force acts on you, which can do either two things. It's either it changes you from the state of rest and make you start moving, or you are already moving, then it changes the way you are moving. It changes the way you are moving. So this is Newton's law, first law of motion. But when we say there is a balance, what happens is that if you are at the state of rest initially, and then you have forces acting in equilibrium, that is, you have forces acting on you, but there is a sort of balance in the way the forces that are acting on you. There is a balance. So what's going to happen is that you're going to remain at rest, or you're moving in a certain way before, and a force decides to come and act on you to change the way you are moving. If there are other forces in the system that are checking and then keeping this force that wants to change the trajectory of your life, if there are other forces in question and they are keeping it in balance, what happens is that you keep moving the way you are moving. And that leads me to talk about the fact that equilibrium is more like resultant as well. It's more like what we have talked about, forces and all of those things. The only different thing is that when we are dealing with equilibrium, we said resultant force, which is F net, we said it is equal to what? Mass times acceleration. As long as there is a net force acting on the body, there will be mass. Of course, the body has a mass, and then there will be acceleration of the body. But when we talk about equilibrium, what we're talking about is that no matter how many forces are acting on a system, the net force is going to be zero. That is, if you join the whole system together, and the system is in equilibrium, the net force is going to be equal to zero. And what does that imply? Since mass will not be zero, this guy cannot be equal to zero. It cannot be equal to zero. So therefore, it implies that that body is going to have zero acceleration. So the bedrock of equilibrium is that a body that is supposed to accelerate will not accelerate. So back to what I've taught you in motion. The concept of acceleration is in two places. If a body is not accelerating, we can define it in two ways. Number one, the body is not moving. The body is not what? Moving. That is, they remain at rest. Or the body is moving, but they are moving uniformly. So if a body is remaining at rest, or the body is moving uniformly such that the velocity of the body remains the same, a constant velocity kind of motion, then the body will have no acceleration. So that brings us back to the fact that equilibrium can actually be in two forms. You can have equilibrium where you remain at rest, and you can have equilibrium where you are still moving. One is called the static equilibrium. One is called the static equilibrium, and the other is called the dynamic equilibrium. The dynamic equilibrium. So that is the concept of equilibrium. The general equation of force, net force is ma, but when equilibrium comes in, F net force equals 0. Now, in this net force that is equal to 0, there's now something that I want you to take note now. There are two major guys that are actually fighting each other here. Number one is the resultant force. The resultant force. So let us assume that there are a set of forces acting together, and these forces, they are not acting at equilibrium to each other. They are just combining all of them together, and then they give a result. So if you have a resultant force, obviously, like I've illustrated now, there is no such thing as equilibrium. There's an action being performed, and there is acceleration. Now, with the several forces now, resultant force we say is the single force that represents all of them. Then what is now going to keep this system in equilibrium is also more like a single force. Now, this single force now, what it does is that it doesn't care about all these other guys, all these other forces acting. What it cares about is what is the resultant of all of them. So the first thing it does is that it matches up in magnitude. So this force that is coming, it matches up in magnitude with the resultant force. And number two, it opposes the direction. It opposes the direction in which the resultant is acting. It opposes the direction in which the resultant is acting. So therefore, the name of this guy is called the equilibrant. The equilibrant. So the equilibrant is that single force that also tend to what? Tend to negate the action of resultant force. It tends to negate the action of resultant force. So for example, if you have a system of, let's say, two forces now. So you have a force acting in this direction. Let's call it F1. Now, of course, this force is going to have a form of equilibrium, a form of resultant is moving to the left. So if you introduce a second force, now and call it force F2. Now, this force is capable of putting this guy in equilibrium. How will it do so? Number one, the two of them will have the same magnitude. And as you can see, F1 is to the left, F2 is to the right. So if both of them are of the same magnitude, obviously there will be no net action here. What if we have two forces? We have force F1, we have another force F2. So this is F2 and this is F1. So if these two forces are acting to the left, automatically there will be a resultant. So all they need is to be in equilibrium is the introduction of a third party, and that is F3. F3 is going to be their equilibrant. But this is the amazing thing. I said F2 is the equilibrant of F1, but at the same time, F1 is also the equilibrant of F2. In this place, F3 is the equilibrant of the net action of F1 and F2. But F1 is also the equilibrant of the net action of F2 and F3, while F2 is also the equilibrant of the net action of F1 and F3. So we always think, well, if a system, as long as a system is in equilibrium, you can always pick one of them, and you are sure that that one that you are picking, that single one you are picking, is going to be equilibrant of every other guy there. So meaning, if you have several forces given in a system and you have to look for one, and that one, and the system is said to be in equilibrium, the system is said to be in equilibrium, all you have to do is you can just find the resultant of every other force, and that will be the same magnitude with that one force that is not known. I'm going to show you what I'm talking about very soon. Now, that single one is going to take the value of the resultant, and the only difference is that it's going to be in opposite direction. It's going to be in opposite direction. So that is what the concept of equilibrium is all about. So the concept of equilibrium is all about making the net force or the resultant force equal to 0. So I'm going to clarify something now before we go. You can see that I've been talking about resultant force in like a separate way, and then talking about equilibriant. Also, I've been kind of talking about resultant force while I'm including equilibriant. So this is what is going on here. Now, if you are considering an entire system and the system has forces A, forces B, force B rather, and then it has another one which is C. Now, if I'm considering this system now, and this system is in equilibrium, then the net force, that is the summation from A, B to C, the summation of all the forces A, B, and C will be equal to 0. And so therefore, the net force of A, B, C, the resultant of A, B, and C is equal to 0. But however, if I want to talk about a resultant in kind of isolation, so I can also say that I have a system of A and B. I have a system of A and B. Of course, A and B, they cannot be in equilibrium because there will be an action towards any of these places. So therefore, I now want to introduce something to them. So this, their particular A and B, we have a resultant force that is not equal to 0. So introducing this now, it counterbalances their resultant force. That's exactly what I'm talking about. So if I'm considering the three as a system that is in equilibrium, of course, their net force will be equal to 0. But if I'm considering just a separate two of them, like in this case now, then the third one is going to be the equilibriant. And so the A and B, we have a non-zero resultant force, which C is coming to counterbalance. And that is exactly what that is about. So quickly, I'm going to teach you how to solve problems like this. So if you have a vector A, B, and C, and they are acting at equilibrium to each other, how do you really solve this? So I will teach you how you can turn this into a triangle, and then you can use any of the sine rule or cosine rule to be able to solve that. So for in the first case, let's say we are given the angle between these. So C is meant to be the equilibriant. So what you're going to do is that there's this thing that I've coined together is called the concept of fixing. So you fix one, you extend, and then you reorientate. So fixing, extension, and reorientation. So this is one of the ways you can actually turn concurrent forces. You can turn them into a triangle that is form a plane with them. So what do I mean by this? I'm going to explain one after the other. Now, we have fixing. What does it mean to fix? It is choose any of these three guys and fix them in position. Leave them the way they are. Don't do anything to them. I always advise when you are fixing something, you should always choose something that has the angle subtended with them. So in this place now, if I want to fix anything, I will choose either A or either B to fix in this situation. So the next thing you want to do is that you want to extend. The next thing you want to do is you want to extend. So what is extension? If I fixed A, so let's say A is fixed. A is fixed. Next thing I want to do is extension. What is extension? It's basically you picking any of these two, either C or B. When you pick either C or B, what you're doing is that you're going to go to the place where they join with every other force and you extend them away from where they meet the point. What do I mean? If I pick B now and I want to extend B, so I'm going to go here to the point where they meet and I'm going to draw a line that seems as if this is where B is coming from. So can you see that now? So what I've done in this case, I've been able to do what we call extension. Extension. This one is fixing. Then lastly, reorientation. So what you want to do is that you want to carry this last guy so that it joins the other two things that you have done. You have fixed, you have extended. So this is the fixing phase. This is the extension phase. So reorientation now is to carry this and bring it to this place. And with that, it will complete a triangle. So for the purpose of this, I will return this back. And I will just draw another one. I will just draw another one. So this reorientation is coming here. Now, the arrow of this is also going there. So I can draw the triangle out now. So you can see we have a triangle, something of this nature. Yes, this is what the triangle looks like. And in this place, this is your C. Sorry. This direction is your B. You can see that this is B. And going down here, you have your C. And then here, you have this arrow going up. You have your A. The next thing you need to determine is what you need to determine one angle there. So if you notice very well, this is a straight line. And if this is a straight line, that means that sum of the angle here is going to be 180 degrees. So if one of them is already theta, and that is the angle between this, which is B, and A. So the angle between them is going to be 180 minus theta. And so with this, you are going to form a perfect triangle. I want to show you something there. If you look at the arrows, you see that the arrows, they are forming a kind of loop. This one is saying go this way. When you get to this junction, this one is continuously leading you in kind of this similar direction. When you get to this junction, it's leading you. So they are kind of entering each other. In the case of resultant force, if these two are moving in this direction, then this A will be opposite. If these two are moving in the same direction, this C is going to be opposite. So what I'm trying to say is that in the case of equilibrium, you can see the way the three of them they are going. So that is that for that. So back to this now. I've been able to form a triangle. Anyways, if you want to see me use this to solve a particular an actual problem, you can use the link that is popping up now. There's a particular solved problem which I explained with actual numbers, and I did proper solution here. So just use the link to get access to the video. You can just get access to the video, save it for later, and then you watch it after the end of the class. So that is the summary of equilibrium. I've talked about dynamic equilibrium. I've talked about static equilibrium as well. So take note of that. Now let's go to moment. What is moment of force? Now, moment of force is simply the turning effect of a force. Turning effect of a force about a fixed point. So before you can observe a moment of a force, the first thing you notice is that it's a moment of force. So therefore, there will be presence of force. So force is going to be there will be application of force. And the next thing you notice is that in the definition I give now, there is always a fixed point. There is always a fixed point. So the moment you are coupling force and a fixed point together, then you are going to produce moment of a force. And that is the what? Turning effect of a force about a fixed point. So what are we talking about here? Is that if I fix a point here and I kind of extend a particular arm length, and at any of these places, I decide to apply force, what is going to happen is that this particular body right here is going to rotate about this point, is going to rotate about that point. And what has happened there is what we call moment. So for instance, if I decide to act this direction, like make this force act in this direction now, what's going to happen is that this body is going to rotate. The body is going to rotate in that direction. It's going to rotate. So more like this. So this is what I'm going to do. So you can have this now. So if I apply force now at the tip of my pen, you can see that the body is being rotated about the fixed point. It's being rotated about the what? About the fixed point. So that's exactly what we are trying to say here about moment of a force, turning effect. Now, so in this place, it now gives us a kind of thing. From here to here, there is the length. We call it R. So the arm length of moment. And then here we have the force being applied in that situation. But another thing again is that the force, you can have it being applied at a certain angle. Let's say that angle is theta. So therefore, what is the general formula for moment of a force? So moment of a force is force times the perpendicular distance. Force times the perpendicular distance. The summary of this is that your force is regarded to as the perpendicular component with the length of the length from the fixed point. What I mean is that, so when you trace your force, when you trace the point of action of your force, this place now to this place, which is the fixed point, the force is acting perpendicular to that line. So this line, the force is acting perpendicular to that line. So this distance, this perpendicular distance multiplied by your force is what is given as the moment. So therefore, if you have it inclined at an angle, let's say theta now. So the first thing you have to always do is that you resolve it to the vertical component. So and when you resolve this to the vertical component, what are you going to get? This is going to be F sine theta. So at an inclined angle to the horizontal, your moment become Fr sine theta. Fr sine theta. And so that implies that the moment is going to be maximum whenever you have theta to be 90 degrees. And it's going to be minimum whenever you have theta to be 0 degrees. That is, the force is acting all parallel to the to that moment arm. We call it moment arm. So, but if the force is acting perpendicularly, you have a maximum turning effect, which is moment. So let's proceed now. So this now leads us to the concept of taking moment about a point and all of those things. So how do we take moment? How do we, answer different problems and all of those things? Okay, so let's get right into it. So if you have a system now, let's say a rule is balanced, or a beam is balanced on a knife edge. So let's say we have this beam is balanced on this knife edge. Now, you can have several forces acting in this system. So I'm going to start with the very basic ones. So you can have a force acting downward here. And you can have another force acting downward here as well. This is F1. What is this guy trying to do? This guy is trying to pull it down from this end. So therefore, the body can actually be slanted and rotate in this manner. But you notice that this other force, let's call it F2 now, is now acting to counterbalance that effect. So therefore, this F1 wants to turn, but F2 is not turning. And there you have what we call equilibrium with moment. So there is moment, but there is equilibrium, meaning that there's supposed to be a turning effect, but because of equilibrium, there's no turning effect. So these things now, we now come about some things that we call the principle of moment. And the principles of moment, we have that the number one is that sum of clockwise moments is the same thing as sum of anticlockwise moment. That's the first principle that we take note. The second one is that sum of upward forces equals sum of downward forces. Sum of upward forces equals sum of downward forces. Now, these two are the basic principle of moment, and if you apply them correctly, you're going to be good. So, what are we saying exactly? You consider each of the forces and then you take their moment. So, in case you have F1 in this case now, so you look at the distance this is from the pivot, or from the fixed point now. So let's call this one R1 and let's call this one R2. So this is what you need to do. Whenever you want to solve a problem like this, you do a sort of analysis. You write clockwise first, then write anti-clockwise somewhere here. And then you take each of the forces one after the other. For instance, you're taking F1, and then you look at the way it's going to behave about the fixed point. So what I'm going to do is that I'm going to fix this now. Imaginarily, let's say you are fixing this point. You can place your finger at this point now. So while you are watching the screen, you can place your finger at this point, and also try to let your arm, your other hand, maybe your left now, let it act in the direction of F1. So if it's acting in the direction of F1, in what manner will this F1 rotate about the point you are fixing? It's going to rotate anti-clockwisely. It's going to rotate anti-clockwise. That is, this F1 is going to turn in this direction. So if that is the case, then you place it here, and the moment will be F1 multiplied by R1. Similarly, if you fix again and you decide to do for F2, you see that F2 is going to rotate in this direction. And what is that? It is clockwisely. So you have F2, R2. And those are the only two forces that are there in the system. So based on the principle of moment, and because this system is in equilibrium, so that implies that F1 R1 equals F2 R2. And that is the principle of moment for you being in equilibrium. However, this is a very simple one. So what if we have very, very complicated ones, like something of this nature? So let's take it up a little bit. So if you have this, so let's say you have forces acting like this. You have a force. So this one is just like the normal one, F1, and then you have another force. Let's say this one is F2, and then you have another force. Let's say this one is F3. Each of these guys, so this one is at R1 away, this one is at R2 away, and this one is at R3 away. And it is said that these three forces, they are keeping the system in equilibrium. So how do you do it? So let's say, for instance, the angle that you're given here, yeah, you're given that this one is acting at an angle theta to the vertical. Angle theta to the vertical. So how do you take the moment of this? It's still the same thing. Just say clockwise and say anti-clockwise. Clockwise and anti-clockwise. So begin to identify them one after the other. So F1, from what we did earlier, you know that F1 will be anti-clockwise. So that will be F1R1. And F3 will be clockwise. So let's not waste our time on those two actually. So that will be F3 multiplied by R3. So now the last one, now we don't know where it will go. Will it go to clockwise or will it go to anti-clockwise? So let's see. In this situation, the first thing you need to do is that resolve it to the vertical. And if you're resolving this to the vertical, you're going to actually get F2 cosine theta. I know, oh, I used sine in one place, I'm using cosine here. Why am I using that? It is one of the things that we have covered already in one of the classes. So if you need to check that out, just use the link that is popping up right now. You will be able to see the video on how do you determine whether one is sine or one is cosine and all of those things. You get to see everything there. So I'm not going to be wasting time to explain that here. So now you have F2 cosine theta. So let's do the fixing again. So if I fixed at the pivot, then I try to act in the direction of this. So where will it rotate? You can see it's rotating this way. And that is what? Counterclockwisely. It's rotating counterclockwisely. So therefore, I'm going to put it in this place. So that will be plus F3. Okay, sorry, that's F2 rather. Plus F2 cosine theta multiplied by R2. So with this now, if I now apply the principle of moment, then I'm going to have that sum of clockwise equals to sum of anticlockwise. So F3 multiplied by R3 equals F1 R1 plus F2 cos theta multiplied by R2. So you can just put R2 here. F2 R2 cosine theta. And that is that. So one last thing before we go is whenever you have more than one pivot, in a system like this and you have more than one pivot, so how do you deal with such? How do you deal with such if you have more than one pivot? So this is where I would like to inform you that, first of all, whenever you have more than one pivot, or in fact, anytime there is a pivot at all, anytime there is a pivot, one of the things you should always take note is that there is always a sort of upward action. There's what? A sort of upward action. That is, you are going up. Or as this body now is resting downward, there is a form of what? A form of action upward as well. That is making this guy to balance both upward and downward. And so for every pivot, there is always a reaction there. So let's call this one R1. And let's call this one R2. So at every pivot, there's always an upward reaction. I'm going to repeat that. At every pivot, there's going to be an upward reaction. So now, what do we do here is that for every other forces that are acting in the system, so we can have, let's say, F1, we can have, let's say, F2, and we can have, let's say, F3. So for F1, F2, and F3, let us assume that. Now, so what we do is that whenever you want to deal with a problem like this, you don't need to stress yourself. Just assume that one of the pivots does not exist. But what you cannot assume is that their reaction does not exist. You let their reaction be in place. So what am I trying to say is that the same system, you work with it, but this time around, what you want to do is that, let's assume that this particular pivot here, sorry about that. So I'm going to move this away. So we assume that this particular pivot here, it does not exist. Then we assume that this is the system we are dealing with. So what you do is that You take the moment of everything here. And so let's take the moment now. So let's say from this place to this place is R1, this place is R2, this place to this place is R3, and between the two of them we have just R. Now, let's take the moment of clock. So we have clockwise, we have anti-clockwise. So let's take F1. F1 is definitely going to be what? Anti-clockwise. We've already settled that. So that will be F1, R1. F2 and R3, they are on the right hand side. They will definitely be clockwise. So that will be F2, R2 plus what? F3 plus, F3, R3. Now, there are two other forces now in this case now. Reaction 1 and reaction 2. But reaction 1, you don't need to bother about it because it's acting at the pivot exactly. You can see that all these ones, they are at a distance, some R away, R1 away from the pivot. This one is R2 away. This one is exactly at that point. So therefore, the distance is going to be 0. So the moment of R1 about its own pivot is going to be 0. It's going to be 0. So therefore, we can only take moment of R2. And so R2 now, how will it act? You can see the way it will move. What direction is this? This is anti-clockwise direction. Anti-clockwise direction. So therefore, you just put R2 here. So R2 multiplied by the distance between it and the pivot between R. Then you multiply this thing. So this implies that F2R2 plus F3R3 will be F1R1 plus R2 times R. Then you do all of this and you can solve for your problem. But here's also the thing. Sum of upward forces R1 plus R2 will be equal to F1 plus F2 plus what? F3. One last thing I did not mention before I go is the set that I will need to mention before I go rather is called the center of mass. Center of mass. Sometimes it is also called the center of gravity. And then what is the center of mass of an object? It is the point where the mass seems to be concentrated, or if it's going to balance, if it's going to be in equilibrium under the action of just its own weight only, its weight is going to balance at the center of mass. That is why we have what we have uniform bodies. We have uniform bodies coming. So we have uniform bodies and we also have non-uniform bodies as well. We have uniform bodies and we have non-uniform bodies. Okay. So back to this place. We have uniform bodies and we have non-uniform bodies. So uniform and non-uniform. What does it mean for a body to be uniform? It means that it is the same in composition all through. If you have this object now, so let's say this is the object, and if this object is uniform, that means that whatever it is composed of at this end is the same thing that it is composed of at this end, is the same thing it is composed of at this middle point as well. But if the object is non-uniform, it can look like this. It looks like it's uniform. But it's possible that it has more content at one side, and at this side, it has lesser content. At this side, it can have different type of content. So in this case now, you don't have a kind of uniform distribution of the content of that body. So therefore, you say it is non-uniform. So what I'm trying to say is that there is what we call geometric center. Geometric center in this case is just going to be the center of this guy by virtue of geometric measurement. For uniform body, their geometric center is also the same thing as their center of mass. That's for uniform body. For non-uniform body, their geometric center is not the same as their center of mass. So please take note of that. So therefore, if you're dealing with a problem and then you are given a beam, and if it happens that that beam is uniform, and then they said the beam has a particular weight, then therefore the weight of that beam will act just exactly at the center because it is a uniform beam. That statement is very, very important to notice in question. But if it was not said that it is a uniform beam or a uniform body, do not jump to place the weight, the action of the weight of that body. Do not jump to place it at the center. Always read further in the question and place it appropriately. Now, so there's a general formula for center of mass, which I'm going to give you in this video. So that's center of mass is summation of mi xi divided by summation mi. What does this mean? It means that if you can pick a point, let's say I'm picking this as a reference point now, and then I have several other masses acting at a point away from this. In that situation, I can do, so if I say the distance from this place to this place, I know the distance from this place to this place, I know the distance from this place to this place, I know the distance from this place to this place. Under the action of those, every guy here, I want to place a pivot somewhere so that the whole thing is balanced. That will be my midpoint. That will be my center of mass rather. So what do I need to do? Just be multiplying each of their masses. So let's call this one mass 1. It can also be weight, oh, so you can also use weight. So it can also be summation wixi over summation wi. So it will be m1 x1 being the distance of that m from this particular reference position, plus m2 x2 plus until you reach the last one. So let's call that mn xn divided by summation of all the masses. Summation of all the masses. Now, if you're using weight as well, just change from mass and change to what? Change to weight. That is how you find the center of mass. By the way, like, you can use the link that is popping up to see some practice problem on this particular concept. Also, if you have not been following the class from the beginning, you can see the playlist. Just check the playlist out and then go through the topics that we have done in the past. And I want you to also subscribe to the channel, like this video, place a comment there. Thank you. I'll see you in the next one.